So I think we'll go ahead and get started. And it's my pleasure today to introduce Wes Hipke. He was going to talk to us about managed recharge in Idaho. A brief review of Wes's bio. Wes has been working more than 30 years in hydrogeology, and most of it focused on recharge. And he spent about almost 20 years developing a recharge program and managing a recharge program in Arizona, and heading up the modeling section in Arizona, and then moved to Idaho and is the manager of the recharge program in the state of Idaho under the Idaho Water Resources Board. So I've been extremely impressed with what they have been able to accomplish the last few years in storing up to 500,000 acre-feet in the Snake River Plain Aquifer. And I think Wes is going to describe the program to us and how it has developed over the years. Thank you so much, Wes.
Oh, thank you. It's really a pleasure to be here. So my intent today is to give you an idea of kind of the situation, some of the background that we're dealing with, and it's going to be a fairly high level. Please write down all your questions. I'll do my best to answer them at the end, just because that seems to work better for these Zoom meetings. We'll kick off and we'll go from there. Okay, so what I'm going to cover is a brief background on Idaho water, what we're dealing with here, because that's one thing I've learned is every place is different. Talk about how we manage water up here, a little bit of the background as far as the Eastern Snake Plain Aquifer and the history, the problem that we're dealing with, and of course, what I'm interested in is the managed recharge portion of that and some results and monitoring. I'm not going to go into a lot of details about the monitoring, but that is one thing I just can't stress enough, and you'll probably hear that throughout. So, Idaho has a lot of surface water. We are really lucky that way. Approximately 60 million acre-feet per year. This gives you an idea of the water that we have. The Snake River is by far the most, but there's a lot of others also. So we have a lot of water, and of course it's just making sure we have it at the right place and the right time. So far as aquifers go, and especially given talking to a geology group, I was actually happy to be able to talk a little bit about geology for a change. Not going to go into any really great depth. The thing about Idaho is, unlike the Midwest, it's not like we have an aquifer underneath our whole state. It's very limited. The other thing is, by far the most of it is basalt aquifer, which that was kind of a new concept for me. There is some alluvial. And as far as the groundwater, even though we have a lot of surface water, 2% of our daily use comes from groundwater. It's 92% of our drinking supply, and over half of the irrigated acres is from groundwater. So it's still a very important source of water here in Idaho. So we're going to be talking more specifically about this Snake River Plain, which you'll see at the bottom down here, and even more specifically, the eastern part, which is this part right here. To kind of orientate people, right over here is the Tetons and Yellowstone. So, far as water management, Idaho's actually kind of broken up into two separate groups, in a way, as I say hesitantly. We have a water resource board that's 8 members, and they're appointed by the governor, and they look at the long-term vision, policy, and they can actually start water projects. They can finance water projects, they can own water projects, working at state agencies and other places. I was like, wow, that was kind of again, a new concept for me. Now, there's also the Department of Water Resources, and one of the things, they're mainly in charge with the administration of water rights and performing other regulatory functions. And of course, they're the main technical arm. The water board is just the 8 members. So it's the Department of Water Resources that supplies the employees for the Water Resource Board. And I'm one of those. My paycheck is from DWR. However, all my work is for the Water Resource Board. Water rights. So water is property of the state in Idaho. You have to have a beneficial use to use it, and those are predefined. Recharge is one of those uses. Prior appropriations, first in time, first in right. And also there's conjunctive administration. We've used surface water and groundwater as hydrologically connected. I'm not for sure what Texas is. I know in Arizona, that actually was not the case, which makes, from a scientific standpoint, life really interesting. And the conjunctive management, this is what it can look like on the, you know, on the plain. You have the upper area with the ag going on, junior groundwater pumpers generally. And then in the canyon, you'll have the surface water users that are generally senior. And this is a fish farm. So background and history, moving right into the ESPA. So again, this is our area. Boise's over here at this part, and it extends through here. It's basically 10,000 square miles. It's one of the largest in the United States. It, I believe, ranks 6. It's high plains desert. We only get 8 to 12 inches. However, in the mountains surrounding it, both up here and pretty much all the way around it, especially over here, where the Tetons are at, up to 60 inches of snowfall per year. So the reason this area is important to Idaho, basically a third of our economy comes from this region. 60% of our irrigated acres. Idaho is a very big ag state. And what I mentioned earlier, there's the aquaculture facilities. Along the Snake River in this area, 75% of the nation's trout comes from this area. We're third largest as far as milk production. There's also a lot of agricultural processing, such as Cliff Bars, Chobani, etc. And in the Snake River as a whole, not just the ESPA, it also produces 50% of Idaho's power. And so that's cheap, green, the electricity that's, of course, really important to the development of the state. So, don't get to show this a lot. It's a very general cross-section of what we're looking at. So over here's the eastern end, and you'll hear me talk about the Thousand Spring area a lot. This is the eastern end of the aquifer, and this goes basically up to the Wyoming border. So it slopes all the way down. The aquifer is basically all basalt, fractured, fuggy channels. I can't stress how much this makes it look nice and simple. This aquifer is not. It's a really complicated aquifer. And I think one place that really shows that, this is a water level map. And you can see by the contours, there's a lot of stuff going on. High slopes up here, flattens out, another drop here. And it's mainly basalt aquifer, but especially in this region up here, there's a lot of perched aquifers that we also have to deal with. This aquifer leaks, and it leaks a lot. It leaks in what's called the American Falls Reservoir area. It comes out here, and then down at the Thousand Springs down at the end. Okay, so a little simple diagram. This is probably very simplistic for a lot of people here, but it does have some points as we go through it. Our water mainly comes from the mountains, from the snowpack. It generates there, comes out the streams. Of course, they leak into the aquifer. And then the Snake River itself has gaining and losing reaches along it, so that contributes to the aquifer also. And water flows in, water flows out. So through a lot of, most of history, it got a nice equilibrium. Everything's doing good. And then people moved in. And of course, to start with, they moved along the river. It's much easier to, when the water's right there, especially being in a semi-arid environment. As more people moved in, so those were your senior water rights were right along the river and generally the surface water users. As people came in, this land's taken, so it's like, okay, they built canals across the plain, going across these lava fields. It's The engineering behind it always just fascinates me. And they develop more agriculture out on the plains. Put water on it, things grow. Not the best soil sometimes, but it still works. And through the ag recharge, pretty inefficient canal type stuff, you know, like 50%. And with the canals, a lot of water went into the aquifer. As time went through, pumping came in, more people, cities, it developed. And of course, that started taking stuff out of the aquifer. And very simply, as probably everyone on here knows, the storage in the aquifer, input minus output. If you have more going into it, it builds up, more coming out, it leaves. So with that aquifer concept, here's how it kind of works as we go through. Here's some of the key things. So water comes out as surface water in this area, travels down. This is where a lot of the surface water users are. They're actually all up along here, but here's some of the oldest. And there's a dam here, Milner Dam. By law in Idaho, we can take the Snake River to zero flow there. So we can use everything up above it. And right below there is the Thousand Springs area where water comes back into the river. Now, usually there's still water going past here. In the summertime when heavy ag is when it's the highest. But even then there's usually some flow that goes through here. And then this, the other key point is there's Swan Falls Dam. From a water right standpoint, there's limits that have to be met here. If these limits aren't met, any uses, surface water and groundwater, all up above here, could be curtailed, or what's called here in Idaho a water call, where if a senior water right's not getting their allowed, they can make a call to have everyone reduce. It's usually not that simple, but that's the basic concept. Well, even though we can take water to zero here, this Thousand Spring areas really adds a significant flow in here. And really, through the whole area, there's hydroplants. So even past this area, even through what's called the Hells Canyon, which is here, along the edge of Idaho, and then into Oregon and Washington, there's a lot of hydroplants. And that's where that cheap green energy comes from. So I want to show you a quick picture of the Thousand Springs area. If you're a rock and water person, if you ever get up here, highly recommend it. It's absolutely gorgeous. You have the basalt cliffs and the water just coming right out of it. Now, the other key part in this system is we have a reservoir system. 4 million acre feet can be captured in it. It doesn't always fill. And all the water right that's stored behind there is accounted for. There are storage rights on it for agriculture, et cetera, et cetera. That adds another complexity to managing the system on how best to use the water and when, given the legal restraints of the water rights. This gives you an idea of where the ag's occurring at. That's in green, and the yellow's all the canals, which from the recharge standpoint actually end up playing an important part in my story. Okay, so what problem do we have? So this is aquifer storage, starting back in 1912. And so this is, you know, people started moving in the late 1800s. 1900s is when a lot of those senior surface waters came into play. More people came in. They moved a lot of water out onto the plains that soaked into the aquifer, and it built up significantly. So in between this time period, the aquifer gained 450,000 acre feet per year. And of course, after that, it declined. A couple things going on here. One, around 1952-ish, the turbine pump was invented. It affected the West significantly. A lot easier to drill that well and pump that water out than manage a canal and move it all across the plains. Those went in. Water became there was some droughts, became water a little more scarce. So ag became more efficient. Well, same amount of more land's being irrigated, more crops being, but it's more efficient, less is going into the aquifer. So with increased ag efficiency, pumping, and droughts, we started this steady decline. Now, so this is conjunctive management. This is the groundwater. Here's the surface water. This is the Thousand Springs area, and you can see there's a direct match. Well, okay, not direct, but come on, that's really close. In between aquifer storage and what the streams are doing. Now, even though we started declining in 52, well, there's still a lot of water. So a lot of water rights were given out in this period here on what one would argue an artificial high. So that's like, okay, what do we do then? Steady decline down, more and more droughts. And yeah, we have the wet periods, great, we build up a little bit, but it constantly stair steps down. So the problem is the senior water rights aren't being met. If they're not being met, they can do a call, they can curtail everyone else. That kind of brings everything to a screaming halt. Aquifers losing about 400,000 acre-feet per year towards the end there. Spring flows were declining. No one's happy, basically. So how do we manage the available water to meet current demands and future growth? So what the Water Board did is it was a stakeholder process, a comprehensive aquifer management plan. Of course, like any government, we have to do our acronyms, CAMP. So the CAMP, it was a really amazing process, and especially coming from different parts of the country. It was everybody. It was the ag groundwater users. It was the surface water users. It was the cities. It was the industry. It was the aquaculture people. They all got together and really kind of hammered out, how are we going to manage this? And so they came together. I'll go through what the key points are in just a little bit. It was passed in 2009. And in that, they also proposed, how are we going to fund this? Because that's the other thing, you start looking at how to solve these problems, it's going to cost money. Interestingly enough, that was not adopted, which I'll talk about that in just a little bit. So what the solutions they came up with is aquifer recharge. Let's take the excess water that we have during the flood events when it's not being stored, because there again, that stored water is already accounted for. When we have that excess, let's put it back into the aquifer. Demand reduction. Of course, that's the first place people go to, and that does make sense, is those junior water users, mainly groundwater, have to reduce their consumptive use. The other thing was, let's kind of reverse what happened in history and they started off as surface water, pumps came in, made them groundwater. How do we change that back? Let's do conversions back, get them back on the surface water. Cloud seeding. Now this was kind of a novel approach, especially back then. How can we augment the amount of water that we're getting? So I'm actually going to kind of jump to the results of that. We did a review of this process just last year. So far as managed aquifer recharge, currently we're adding 280,000 acre-feet per year on average from 2014 to 2020. You'll notice that these years aren't going to match up because of when different things started happening. Demand reduction, so that's 240,000 acre-feet per year. That's actually where the camp worked out this process of how it was all going to happen. What's really key about that document is they figured out what the key things needed to happen. And that's really important because it didn't happen as people thought, but it set the groundwork as people are working through the problems to figure out, hey, here's the goals we can shoot for. So because of a water call from those old surface water rights with the groundwater users, a private settlement agreement was reached where they came up with, here's how much we're going to reduce by. So far as surface water conversions, that was another 87,000 acre-feet. Cloud seeding we're still working on. We're kind of conducting analysis. In the work we've done so far, that makes up, it probably adds in between 5 to 10% water on average as far as availability. So not counting cloud seeding, we're looking at over 600,000 acre-feet per year difference to the aquifer. So remember, we were short 400,000. Well, that's just to keep it where we're at now. So ideally, by adding more in, we can actually start building it back up to get to a place where everyone's current demands are being met. If we're lucky, maybe we can build it past that to actually start adding some more stuff back in. Interestingly enough, the camp estimated it'd take 30 years to reach this goal. So as far as that goes, we're doing amazing. So, brief synopsis, but now what did it take to do the managed recharge portion of it? So going to go through a brief timeline of some of the key things that happened. Managed recharge is not a new thing up here. They started looking at back in the 60s, solving some of the problems. And even starting back in 1980, they started looking at some of that legislation that has to get in place to have a program really work and be successful. Jump another 20 years from 80 to the 2000s. We get our first, they start spending some money on some projects, kind of testing things out. The legislature approves almost $1 million to kind of develop this, and we start doing some recharge. And we start looking at, okay, how can we make this feasible? So this is really the early stages of trying to deal with it, get it on the ground. What's it going to take to have this work? 2000 to 2010, one of the key things in here, you'll start noticing these delivery calls. And really what that means is this was a drought period up here. And of course, water gets really scarce, people going, hey, how are we going to do this? And the legislature is actually very involved here. I personally think that's one of the advantages of having the water board that has that connection. So we start getting some money to start developing more into it. The camp, so after another drought period, they came up with a camp in 2009 and said, okay, here's how we're going to solve the problem. So we jump ahead, another drought period, and I mentioned in 2009, here's how we're going to fund it, and everyone went, ooh, no, I don't want to do that. How about them? You know, and the finger started going every which direction. More delivery calls, another drought period. And the legislature came in and went, whoa, whoa, if this is going to happen, the state's going to have to fund this. We need to get on top of this because this problem is just going to get worse and worse. So they set up $5 million from the cigarette tax. So that's not a guaranteed amount, depends on how much people are smoking, to invest in setting up a program that would have constant funding moving forward, because that's really what it needed for managed recharge to work. For the things they set up in the camp to be effective, those have to go on forever, basically, to solve this problem. We started, so it wasn't until we had that the board could start their full-scale program in 2014. So that's why my numbers started then. You know, like a good, 5 years after it was approved, it kind of took that long to get everything in place. The settlement agreement that started the groundwater reduction didn't happen in 2016. And out of the settlement agreement, one of the things that they recognized for that agreement to work, which if that agreement doesn't work, it starts cutting off water to significant ag portion and the cities, which is like, okay, that's not really functional. For that to work, the recharge program has to be successful. So since the tax money's not guaranteed, they actually set up $5 million from the general fund. That's there every year. A little harder to move that off. So that gave us the current timeline. The things when you're looking at managed recharge, and if this is very fundamental for some of you, I apologize. You need your source of water. And part of that is having the water rights in place. Where is that water going to come from to meet the demands that you need? And that's another key thing, is what problem are you addressing? If you're solving a 10,000 acre-feet problem, that's great. for us in looking at this, it's like, okay, we need to have enough water for, 250,000 or more. And I'll explain a little more detail of why it's more in a little bit. Once that happens is how are you going to get into the ground? Are you going to use basins? Basins are fantastic. They're cheap, and they can put a lot of water in the ground, and they're great if you have the landmass area to do it in, or the infiltration rate. A lot of times you don't, then injections work better. If you're tight on land, these can work. From my experience in Arizona and here, actually injection has worked really well here. We only have one current area that's doing that. In Arizona, it's interesting, there's problems, and you end up with maintenance a lot more so than with the basins. There's other methods such as trenches. I know California is big in doing, flooding their ag land. I have questions about that, but that's a talk for another point in time. Location, okay, great. We need basins, we need that area. You gotta find an area that is gonna go in. And is it gonna have the results that you want? And once you figure out the locations, how are you gonna get the water there? Idaho was really, really lucky. And when the water was available, we had the irrigation canals that weren't being used. That saved us tremendously on the cost of this. Impacts. I can't stress this enough. It is so important to think through what monitoring do you need in place to determine what the impacts are going to be. Is the recharge having the effect that you're going to have? Is it having unexpected consequences? Water quality is a huge portion. So in the Snake River, the board has 1980 to 1998 priority dates. That puts us behind all irrigation, but it puts us way ahead of pretty much anything else. So when irrigation's not happening, or there's plenty of water to meet the irrigation demands, our rights generally kick in. So currently we have 7,700 permitted. In Idaho, you get an application, you get a permit, you prove it up, and then you get the actual license. And we're looking for another 7,500 that we have in the application that we're working through that process. So we have enough water to do what we want to do. Given the reservoir system, there's times that storage water can also be used for recharge. The board doesn't do that because we don't want to be in any competition with any of that storage water that's used for other purposes. But that is a possibility. The water that we use, the Snake, is pretty good quality, low TDS, turbidity, fairly good on the nitrates. And especially most of ours happens in the wintertime. It's been really clean from all the monitoring that we've done. With the water rights, so I have all this water rights available, but you can't use it all the time. So we have a senior water right here, as far as the storage, 1921, another right here for hydropower, 1912. So basically, until water's flowing past these points, it's not being stored, I can't recharge in any of this area up here. So that's only about 50% of the time can I recharge. Below there, I can recharge all the time. One of the key things is, and I don't expect you to read what's on this graph over here, this is about 500 cubic feet per second here. That's the minimum that can go by. So I have rights for much more than that, but on these poor years, the most I can do is about 150,000 acre feet. Given that goal is 250, that means on these big years, I got to put a lot more in to make up for these drought years. So what the board's done is we've invested about $20 million since 2014 on upping our capacity that we can do here. This gives a sample of all the projects that we've done, everything from studies to developing new sites, shows kind of the current ones that we're still developing. A lot of it has been in this region down here because that's where my water is available all the time. This is equally important, but it's generally available only in the spring on those high flow years. In this point in time, we've increased capacity by over 2,300 cubic feet per second, which is huge. And that's taken a lot of work. All the green are sites that we've developed to increase capacity in this area. Like I said, a lot of it's in the lower valley, and there's actually some private going on also. And so what these projects look like, it's a variety of things. Everything from, so this is a pump station that goes into a pipeline that goes to the injection wells. Building basins or recharge sites off of canals. Again, having the canals there is huge. We didn't have to build that infrastructure to get the water to these places. It already existed. Some of these are fairly large infrastructure projects though. The other thing is we've actually built new canals, and we've had to improve the canals that are already there because they weren't designed to deliver water during the wintertime. A lot of freezing conditions, et cetera, puts a lot more stress on things. And the other thing, on some of these on some of these canals, there's hydro plants. Again, they weren't designed for winter recharge. We've had to go in and retrofit those so we can move the water that we need to move. This is the end result of some of the projects we've developed. To give you an idea of the range in size, this is around 120 acres. This one's around 10, 15. This site in the middle is around 322. This one's 200. This site is around 54 acres. Interestingly enough, this is one of our new sites. So this site does around 650 cubic feet per second. This site, being 54 acres, can also do around 500 cubic feet per second, much smaller site. And this is the finished pumping site. This also shows some of the conditions we deal in. All these others look nice and pretty, and the blue water. Yeah, this is more common when we're dealing with a completely frozen and icing conditions, which has caused some interesting issues we've had to deal with. So this is from last year, gives an idea of the recharge that we've done. Max diversion rate was 3,000. We did 150,000, gives you an idea of the location. These are proportional of where the recharge occurred at. We could actually do recharge in the upper valley last year, which is huge up here. This kind of gives you a better idea. So what you're looking, these light blue and medium blue, this is the recharge we did. Here's the water available. So when we started, it was drought years. And in this period here, we were still developing our capacity. And the results that we've had have been great, and I'd love to take all the credit for them. Yeah, we've had some really great years, so I can't take all the credit for it. But you can kind of see with the amount of recharge we can do with the water that's available, it's constantly growing. Still building out here. This is our first year where we could actually have the capacity of using all that minimum flow in the wintertime, that 500 CFS that was available. And even though there was less water last year, the amount of recharge we did is comparable to when we had a really wet year. My standpoint, that's absolutely awesome. So cost-wise, so total, looking at monitoring, equipment, operations, conveyance. So we don't pay for the water, but we do pay for our partners, the canal companies, to move the water and to recharge it. And the capital costs. So that's the infrastructure I just talked about. Conveyance and capital costs pretty evenly split right now. However, this is going to go down as we move forward. This honestly is probably going to go up as we move forward. Because in what we've done so far, we've had some really good years, but we've not been able to really run at max capacity. My estimate as we move forward is this conveyance cost is going to range anywhere from 1.3 million to as high as 8 million. So it's just going to really vary. The monitoring and equipment, that's another one. This is going to steadily go up. When we first started in 2014, we were only spending about 400,000. Last couple of years has been around 500, 600,000. As we develop more sites, there's more monitoring to do. So that cost, like I said, it's going to go up as we move forward. Gives you a snapshot, though, as what it's taken to get this to where we're at right now. One thing I'll say about the cost. So the other thing is we're currently looking at, I just did the numbers, and in between $10 to $20 an acre foot, and that's taken into account amortizing some of this capital cost out. To give you an idea, in other places, in an article from California, they estimated their cost per acre foot for doing recharge. This is a few years old. I know they've done a lot of work out there since then. Was averaging $400 an acre foot, and they had some that was just shy of 1,000. In Arizona, where all the facilities are permitted and they have to go through this regulatory process, they have to prove that they have the economical feasibility to run the site. So now, not counting the cost of water, which I don't know if California includes that cost either, the recharge sites to do the capacities they were designed for, you were probably looking around that $40 an acre foot. One of the reasons that our costs are so cheap is that infrastructure cost of getting the water to these areas. Moving forward to develop new sites, we've got all the low-hanging fruit. Potentially, those sites are going to cost a lot more if we develop any more capacity. So, okay, that's really great. We did all this. Are we having the impact that we want? 1980 to 2015. So we do have a groundwater flow model over this area, and this is developed from that. A lot of red here, over 35 feet of drop, and as far as water level change in the aquifer. So it points to some of those problems we were having. So since that point in time, from 15 to 20, a lot of improvements. All these little dots are all the monitoring points that went into this. We're still working. Now, we've added a lot of monitoring points in the past 5 years. You see these big blank spots here? We're not done yet. We need to add some more. And again, part of this rise is we had some really great wet years that added a lot to this, especially the spring of 2017 was huge. Now, quick animation here. Oops, gotta switch to my pointer. Sorry. As I gotta figure out my mouse, get it on the right screen. Here we go. So this is an animation we've done. It's water level change. So I'm gonna start it here. And so those blue dots that you see forming, whoops. That's recharge that's occurring. So here is Box Canyon, that's the spring flowing out in this region down here. You'll see the recharge that's occurring over here. And this is how the aquifer is changing. So this is 2016. This is in the summertime. You'll notice a lot of green forming. The agriculture, the incidental recharge from agriculture is pretty huge here. And you can see it develop as it goes along. You see the declines happening in the aquifer. As we get into the winter months, you see it going away. And then it starts building back up. This is that really big year, the results, a lot of water coming in. And you can see the stream flows are steadily going up. I'm not so interested in the peaks as I am interested in those troughs on the bottom steadily climbing. That's going to be the key thing. And especially if we can keep them going up or at least stabilize during the drought period. So now the key thing is, like I said, this last year wasn't a really big water year. Where I see recharge impacting is we're able to keep this ridge in place, which normally would have drained off. We keep that in place, and then that also backs water up this way and provides more for the aquifer. The water that's recharged along the river, which right in here, has a tendency of flowing back to the river quicker. The more we can get in these areas, it flows out slower and is really going to help during those dry periods. Adaptive management, I can't stress this enough. the importance of developing the monitoring and tools to assess the impact and effectiveness of the program. As scientists, we're all there. We agree with that. We got to know what we're doing. Is it being effective? I can't stress the other important part of this, being able to communicate to the public and to the legislatures, to the people that are funding this, what impact that you're having. It's crucial for a program like this. Already, and we have to adjust as we move forward and constantly look at, are we having the impact that we want? Unforeseen consequences and concerns. One of the key things here is things are going to happen you would have never guessed. Really quick story is crawfish. I never thought that was going to be a problem. Because we're using the canals all winter long, the crawfish don't die out. They exploded. They drill into the bank, hit a varmint hole, water hydros through it, sloughs off the canal bank. Not a good thing for canals. Never thought that was going to be a problem. Changing conditions, both natural and political. I'll show you some really great results, and it's interesting. One of the things we're looking at now that we're having to deal with is the power companies are going, oh, hold it. How is this affecting us? Again, the importance of having the monitoring in place to be able to work out what's actually happening and giving the information to the policymakers that they need. So with that, any questions, and I will stop sharing.
Hi, Wes. We actually had a couple of questions come in. The first one was from Ramon Trevino. It's, has Idaho received pushback from downwind states regarding like cloud seeding?
And so what's the question about there? Actually, so what's the complaints?
Ramon, feel free to unmute yourself.
Yeah, hi, Wes. I was
Hi.
wondering, when you seed clouds on one side of a mountain,
Yeah.
I would imagine that you're reducing the downwind side of the mountain precipitation. I was just curious if other states have said, wait a minute, you're taking some of our precipitation.
Right. Okay. Disclaimer. I am not a cloud seeding expert, not even remotely close. However, part of the studies that we're working with Idaho Power in doing is actually quantifying some of that. So there's it's called the Snowy Project, which you might be able to Google. I could probably get you some links if you, contact me directly. In the studies that they've done so far, what they've shown that's not the case. It really doesn't affect that precipitation over there. And like I said, I wish I did understand it. I don't understand the science of it. What I've been told is in the studies that we've done so far, that's actually not been the case.
Wes, I have a question for you. This is Bridget. Incredible presentation, and it's just remarkable what you guys are accomplishing. And it's interesting, in the early 1900s, you had all that recharge going on, but we didn't call it managed aquifer recharge then, but it was very fortunate that you built up the aquifer. And I think we've seen this happen in different regions. You worked in Arizona and Idaho, and in each state you helped develop the programs there for managed recharge. How would you compare the processes and the legal aspects and stuff, or was it easier in one state versus another, or what key aspects, demonstration projects, pilot projects, would you suggest trying to get things going?
So it was fascinating because of spending so long in Arizona dealing with recharge. I kind of thought I knew what I was doing. No, I didn't. And it took me a while to kind of go, wow, what's the differences here? It's what's driving the recharge. So in Arizona, what was driving the recharge was California. California has caused more water management than I think anyone else, because the fear was they were going to come and take Arizona's water. So we had to use the water from the Colorado River that went through the canal. That really started the recharge program. And Arizona has a lot of regulations on water use. X amount of groundwater. If you develop a new use, new municipal development, you have to prove up a 100-year supply of water. Well, it's a desert, there's X amount of water. So there, Arizona developed the regulatory framework, not only to permit the facilities, to keep track of how much water went into them, they also created the framework where you could develop credits that could then be used to meet that 100-year water supply demand. So all the recharge that occurred there is really privately funded. The state did some projects to kind of get it going, but it's really privately funding because it makes economic sense because they got to prove up the water. Idaho doesn't have that. And so that's why the state had to step in, because it's like, hold it, if we don't do something here, that's really going to affect our economy in a very major way. So the state had to step in. And so it's a state-run program. Idaho does not have the framework for recharge credits. So any recharge that's done has to be for a specific mitigation in a year. And the recharge we do is just for the benefit of the aquifer. So we can solve this problem. So it's just interesting. It's just really what's the economic factor that's going to drive funding the recharge being done. I've seen the regulatory and I've seen what we do in Idaho. Texas, oh my God, I have no idea.
Okay.
We're working on it.
Yes, it's a good thing to work on.
I think, Teresa, do you want to ask your question? Or Teresa's wondering, can't you eat the crawfish?
Having spent time in Texas and Louisiana, they're not that big, but I would think so, yes. I've suggested that to people. We should open a Cajun restaurant. There's not that many up here, and I really miss that. But so you probably could, but they are pretty small.
So James, would you like to ask your question?
Sure. So with karstic aquifers that are very buggy and fractured, one of the issues we have down here is monitoring where water goes when it's recharging. You have, in this project is much more regional scale, but have you had any problems monitoring and where if your water was recharging, or rather it was the natural water, and how have you gotten around that? Because that's always an issue down here when you're talking about the karstic aquifers.
I think I've not worked a lot with karstic aquifers. It would be great to have a more detailed conversation. I think we're more similar than what you think. Mm-hmm. With basalt aquifers, it's kind of the same thing.
Yeah, that's what I'm asking, if there were any concern, like if there were any things you had to do specific to monitor them, because it can be unpredictable. So.
It's been a pain. To put simply. So one of the things that we've done is we have an active dye testing program.
Okay.
And so we've used that, which has been huge because we put wells that make complete sense that it was down gradient and right in the pathway, and none of the recharge water went there. Mm-hmm. No. The dye has helped us of making sure we're doing the monitoring in the right place, that we're actually doing that. And it also helps us dial in how fast this water's moving. I've seen K values over 1,000. Yeah. Feet per day, which I'm like, in my previous experience, I'm like, holy. So, and it is tricky. I think my imagination would be karst would be worse. But by dye testing has helped. And we've got this regional program set up, but that's one thing the recharge program is doing is more specific site stuff, transducer data, so we can get more of that hourly, so we can start mapping this closer to try and figure out where it's going and what it's doing. Not a great answer, but that's what's given us the best results so far.
Okay. Thank you.
Sure.
Go ahead, Linda.
Hi, Wes. Thank you. I enjoyed your talk. Very good.
Oh, thank you.
Congratulations to good results. I just had a question about any strategies that you found successful in communicating with decision makers. And I kind of take it from your comments, it wasn't a geologic cross section.
No. It's really interesting, and I report to the Water Resource Board, which are 8 individuals that they're very knowledgeable, very smart people. None of them are hydrologists or geologists. And this is only one problem that they're dealing with. They're dealing with the whole state and a whole variety of issues. And we have spent a lot of time looking at how do we get this information to them that's going to make sense to them. And to a certain degree, that animation I showed, that's partly why we came up with it. That animation incorporates a lot of different information. You wouldn't want to use it for a scientific purpose.
Yeah.
But it allowed people to see what was going on. And so the more visual, simplistic, especially being scientists, the more because we have the tendency of overdoing it. I do cross sections and I love hydrographs, and no, don't go there. So the more simplistic and visual you can make it, the better off that you are. The other thing that I found is you need the tools to do that. So you need that data back there that can drive those type of animations, those simplistic tools. Because it has to be relatively accurate. You don't want to give them bad information. But I think as scientists in dealing with the public, and especially with the policymakers, we have the tendency of making things too complicated. The simpler you can make it, the better.
Thank you. Thank you.
Sure. Good luck.
Sarah, do you want to unmute yourself?
Sure. Thank you so much for the presentation. I was curious if y'all encountered any issues related to contaminant mobilization from the aquifer. So things like metals, nitrates from ag, and if y'all generally just had experience or guidance with how to incorporate that into the planning and design of the projects.
The first thing I'll say is when you go to plan and design it, goodness gracious, include water quality monitoring. And it's as scientists, obviously we don't want to do anything that's going to harm the aquifer, but there's another aspect here, especially dealing in the areas I'm dealing with and dealing with the general populace. You do something new, if something happens to their well, they're going to say, it's you. This is new and this is what's causing my well to go bad. So you got to have the data to be able to answer that. And it's a reasonable concern. So you have to be able to do that. What we do, so dealing within the laws, it's interesting. So the canals, any recharge that happens in the canals doesn't have to be monitored. However, the off-canal sites that we build do have to be monitored. So we monitor the source water going in minimally on a monthly basis. In areas that are closer, we do that, but we also do bacteria monitoring on a weekly level until we can prove, look, we're not having an impact here. So that's the type of monitoring that we do. The results over the past 5 years of doing pretty intensive is, I think it helps we're recharging in the wintertime, so the bacteria is not bad. Let me come back to the bacteria. Everything else, it's rare to get a detection. So actually the water that's going in has been really, really clean. And the few things we might get a detection of, not over any limits, but just a detection of, we've not seen any correlation with our groundwater monitoring. And even with the fast travel times, at least in the stuff we're dealing with, there is enough filtration going on that even with the bacteria, surface water always has bacteria in it. We don't, if you do enough groundwater sampling, you'll get hits of total coliform. And you'll probably get a hit of E. coli if you do enough of it. Those are very rare that we do get those, and there's no correlation in between that and the surface water we're putting in. So there's enough going on, whether the concentrations are low enough in the surface water and the filtration, everything that's happening, by the time it hits the well, it's not happening. It's like there's none there. In the injection wells that are going on, they have their own monitoring plan. Any hits they got of E. coli it had to do with the separate process. It did not have to do, it wasn't coming from the injection well. So far, ours have been very clean. We sample over 120 analytes. We go overboard, honestly, probably more than what the Department of Environmental Quality asks for, because we have to answer all these questions. There's some metals we do constantly, but we've also just kind of done a full suite of metals every once a year, so we just can show here's what's going on. So at least in the stuff that we've done, we've not, the only impact we've had is a huge aquifer, so its impact we're having is slight. We've reduced nitrate levels. Phosphorus going in is a little bit higher, but by the time it hits the aquifer, we can't see any difference. And those are the only results we've gotten, which from a water quality standpoint, I'm extremely happy with.
Does anybody else have any questions? I think we would like to thank you, Wes, for an incredible presentation, and we wish you all the best in your future recharge program and hope it continues to be as successful as the past few years. It's amazing. And good luck, and thank you for your time.
Thank you very much. Enjoyed it very much. Feel free to get my contact information. If you have any questions, do my best to ask. Good luck in what you're doing down there. I believe it's the right path to go.
Bye-bye. Take care.
Have a good one.